Okay, you're probably familiar with this. What this picture is trying to show us is that we have a prism, and it's made out of glass usually, and then we have light that comes through the prism, and then the light, according to its wavelength, bends to a differing amount as it passes through the glass. It's called refraction. It's different than the diffraction that we talked about earlier. And there's actually a property of the glass called the index of refraction. But the light goes through the glass and it refracts and separates into what we see as a rainbow, or Roy G. Biv, right? So we have red at the top. Let's see if I can actually change it to a color we can see. And then right, red, orange, yellow, and so Roy G. This is blue, indigo, and violet. Okay, so that's Roy G. Biv. A little messy, sorry. Anyways, that's what is caused by a prism. Now, it turns out if you take a lot of different elements, any element really, and you add energy to it, it oftentimes emits light. And so if you take, for example, if you think about a neon light, right? A neon light is really just a tube that's filled with neon gas, and then we run an electric current through it, put a high voltage on it really, and then we get an electric current that goes through it, and that's what gives us the red light. Fluorescent lights are the same way. A fluorescent light really is a gas, and it has a little bit of mercury vapor in it actually, and when you electrify it, it produces the color of light that we see, that we associate with a fluorescent light. Okay, so if you take this light, for example, this is a hydrogen lamp, and it sort of has a reddish pink tint to it, and you pass it through a prism, and you look at the spectrum that you see, you don't see a rainbow. In fact, what you're seeing is they usually put the light through a thin slit, and then the slit goes through the prism, and because the beam of light is narrow, what you only see is specific wavelengths of light that make up that reddish color that we see when we see a hydrogen lamp. You could do the same thing to neon, and you'd see a series of many, many different colored lines. Even a fluorescent lamp, one of the old standard fluorescent lamps, if you run the light from a fluorescent lamp through a spectrometer, that's what this is called. I better change the pen color to something other than white. And a spectrometer just allows you to measure the intensities and wavelengths of light that come through. But a fluorescent light, what you can actually see when you look at it, is you can actually see some of the emission spectrum from mercury in there. Okay, so, and this is just basically what I just said. So here's a helium spectrum, barium spectrum. The hydrogen spectrum, I just left it on here, it's just stuck on here. It's about 4 or 5 lines that you can see. Every element has a unique spectrum. Now, white light gives us a white light spectrum, which is every color, and it's basically what you see when you shine something at the sun. But when you're looking at individual elements, what we see is only individual lines. And if you think about what this means, right, there are no wavelengths of energy in that region. And all the energy that we're seeing is only in specific wavelengths of that spectrum. So other elements that would also do this, here's examples: sodium, potassium, lithium, barium. These all would give different emission spectra if we were to observe them through a spectrometer. So every element actually gives us a unique signature of its composition, of its presence when we see it in a spectrum. So even if we see mixtures, we can often mixtures of different compounds, and we excite them, we can often tell which elements are in there just by looking at the emission spectrum from the mixtures of substances. So one of the people to study this very early on was a guy named Rydberg, and Rydberg studied hydrogen spectra And what he noticed is that you could explain the wavelengths of light that were observed. So these are the wavelengths of light, right? And by using a constant, which is known as Rydberg's constant, okay? By using a constant and then multiplying it by a series of integers, so these are integer values, right? When you subtract their inverse squares. So it's a really unusual, like if you think about how weird that is, when we look at light, this looks very continuous to us. That is, every wavelength of light is observed. But when you take the hydrogen spectra and analyze it, in both the visible, right, and the portions of the light that are not visible, it turns out hydrogen emits light also in the ultraviolet and also in the infrared regions. If you look at the line spectra that are generated, all of those can be fit to a pattern of inverse squares of integers, whole numbers, subtracted from each other. So Rydberg didn't really have an explanation for what he saw, and it really came down to a scientist named Niels Bohr. And Bohr said you could imagine that the atom and its electrons, right, could be modeled by a planetary system, and so we call this a planetary model. Like in a true planetary system, this would be the sun, and then Mercury, Venus, and Earth, and Mars, and all that stuff would be around in here, right? So these would be the planets. The electrons are like the planets in their orbits, right? And the sun is at the center of all that because it's what's attracting everything to it, to the middle of the solar system. Okay, so what Bohr said was, if you had an electron in this orbit and you wanted to push it to a higher orbit like this, you would have to put energy into it. On the other hand, if an electron started here and wanted to go to this orbit, right, then energy would have to be released. So going down, right, would release a photon, but to get it to go up, you either have to absorb a photon, or like we do with the lamps, we use an electric current, and the electric current energizes the electron to a higher energy level. So these orbits were numbered 1, 2, 3, 4, given whole numbers, right? And the energy levels had specific values in Bohr's model. They're actually E is equal to minus RH, so this is the Rydberg constant, which I'll show you in a second, divided by n squared. And Bohr proposed that n is equal to 1 was the lowest energy level, that is the one with the lowest potential energy or closest to the sun. And then as you go out, these orbits would increase in energy. And energy that was released, you could calculate just by calculating, for example, this is E4, right? And this is E2. If you take final minus initial, so delta E, you could just say that's E2, this is your final state, minus your E4. And that would tell you how much energy the electron lost as it dropped from that higher energy level to the lower energy level. So what Bohr determined is that the energy level that produces visible light are all the transitions from energy levels higher than 2 to energy level 2. If you went from energy level 3 to 1, for example, that energy gap is actually so big, it's not shown onto scale here, and I'll show you that in a second. That energy gap is so big that produces ultraviolet light. On the other hand, if you drop from energy level 4, like here, to 3, instead of all the way down to 2, so 4 to 3, that energy is small enough that it's not visible to our eye because it's in the infrared region. So we're only seeing the transitions from n equals 3, 4, 5, and higher down to n equals 2. The energy for the red light of the Bohr model, right, was from n equals 3 to 2. This would be the smallest energy transition. And then the next line that we see is from 4 to 2, and that would be the green light because it's a little bit higher in energy. And then 5 to 2 would be violet. There's actually one other that some people can see if you go from 6 to 2, but people don't often observe that one. It's just really faint and hard to see for some people. So the further the electron drops, the more energy gets released as a photon, right? And this series is known as the Balmer series for the guy who originally sort of identified this line series. So let's go over the details of how you calculate the energy of a photon when an electron drops from energy levels 3 to energy level 2. So to calculate the change in the energy for the electron, that's going to be E final minus E initial. Rydberg's constant has this value, okay, 2.18 basically times 10 to the minus 18 joules. So if we want to calculate the electron energy change, then it's going to be for n equals 2, for example, right? I'll just put a 2 in this value here. So delta E for the electron is equal to minus RH over 2 squared, because that's the final state. So the electron's dropping from 3 to 2, like this, right? And then we're going to subtract the initial energy level, which is minus RH over 3 squared, like that. And then a lot of times people will factor this out and then just do the math. So I'm going to do minus RH times 1 over 2 squared minus 1 over 3 squared. So then I can calculate this value and then just multiply it times RH. Well, actually, yeah. So let's go ahead and pull up a calculator. And you just do like this. You say 2 squared, I'll take the inverse, minus 3 squared, I'll take the inverse, and then I'll hit equals. And that becomes this number, 0.13889. And then I'll multiply it times RH, or minus RH actually. Okay, and then the energy of the photon will be then 2.1799 times 10 to the minus 18 times this value here. So times 2.1799 E18, change sign. And that's the energy of the electron, the change in energy for the electron. So this becomes minus 3.028 times 10 to the minus 19. Okay, so it looks like that. Now, here's the thing. We want to calculate the wavelength of the photon that's released. And so you have to think about how conservation of energy works in this system. You would say the energy of the photon, right, plus the energy of the electron is equal to 0. That's the conservation of energy. So in the conservation of energy, then, we would just take this energy and change its sign, and that's equal to the energy of the photon as it's released. So then we say, right, E photon equals negative E of the electron. So that's just going to be 3.028 times 10 to the minus 19th joules. Now we can calculate the wavelength using the equation. I'll write it up here at the top. E is equal to hc over lambda. I have the energy, so I just need to rearrange it. So lambda is equal to hc over E. And then I can look up the value for H, which is 6.626 times 10 to the minus 34 joules times seconds. And then c is the speed of light, so 3 times 10 to the 8th meters per second, and then divide it by this value here. So rather than bore you with the details of writing all that out, I went ahead and filled it out for you so you can see it. So 6.626 times 10 to the minus 34 joule seconds, that's H. Then it's 3 times 10 to the 8th meters per second, that would be my speed of light. And then this is the energy of the photon, so that I just pulled that from down here. And when you do that calculation, it becomes 6.57 times 10 to the minus 7 meters, or 657 nanometers, if you wanted to convert it over to nanometers. So I wanted to give you a little bit of a picture of how these energy levels actually compare to each other. So let's do a quick idea, sort of thought board here. We're going to have the energy levels, right? Those are equal to minus RH over N squared, like that. Now, what happens when N gets really, really large? Okay, so if N gets really large, then I'm squaring it, right? Then E must be getting really, really small. So when we're thinking about what's going on, if we're thinking about N is equal to infinity, this is zero energy. Because as you divide by larger and larger numbers, the result gets smaller and smaller and smaller. Now, what does it look like when N is equal to 1, right? Well, if N is equal to 1, then the value of E is just minus RH. So I'm going to put that down here. And one of the things Bohr said is that E couldn't be 0. It could just be whole number integers, okay? So this would just be minus RH. So if you think about the way the energies are set up and why Bohr put the negative sign here, is because energy level 1 had to be the lowest energy, and this is how you get it to be the lowest energy. If N is equal to 2, right, then what does that become? Well, then that becomes RH over 4 squared, right? So this is going to be RH over 4. It's approximately, in terms of spacing, about here. This is N equals 2. So now we have RH, negative RH, over 4. This number is closer to 0 than this number is. And then if N is equal to 3, right, then it becomes minus RH over 9. So it's about 1/9. So if we think about this space, 1/9 is approximately here. So this is N equal to 3. This is minus RH over 9. Now, what happens if it's N equals 4, right? N equals 4 is 1/16. And so, it's about, in terms of spacing, about here. So this is N equal to 4. And you notice what happens. Remember we had 5 and 6? 5 and 6 are really close up here. And so you notice the spacing when you start down here. As you go up in energy levels, the spacings of the orbitals get closer and closer and closer. And even though this seems like it's weird, this is the model that fit the hydrogen atom's line spectra exactly. Okay, and I didn't really talk about it at all, but hydrogen also emits in the infrared and in the ultraviolet. And it turns out the ultraviolet emissions are always from N equals 2, 3, or 4, or 5, or higher, all the way down to N equals 1. And you can kind of see why that is using this diagram, because this gap in energy, this is actually the largest gap. So these photons, as they go from energy level 2 to energy level 1, are so much higher in energy that they're not in the visible range. So it just turns out that when it drops to N equals 2, all these transitions in here, going from N equals, let's say, 6 down to N equals 2, those are the ones we see in the visible range. And then if you go from N equals 4 to 3, these gaps get progressively smaller. So gaps are getting smaller. And then as you go up, for example, from 4 to 3, this is going to be, for example, infrared light. Basically heat emission. And so all of these actually have names, like the one that we looked at before down to n equals 2 was called the Balmer series. But the UV light and the infrared light and other transitions all have different names. And they were able to see those lines by using spectrometers and then using film that's sensitive to colors of light or electromagnetic radiation that our eyes can't see. I did maybe a more detailed one here, right, to show all like the RH and stuff. This is a good reference chart to have if you're trying to think about these problems, because it shows how the spacings get closer and closer and closer and closer together. It includes all the way up to n equals 6. And remember, all that Balmer series is from 6, 5, 4, or 3 down to 2. And then everything else is in the ultraviolet down here.